It's my great pleasure to introduce Professor Lara Waldrop. She is an assistant professor of the Department of Electrical and Computer Engineering at the University of Illinois, Urbana-Champaign. That's my father-in-law's alma mater.
Fantastic.
Doesn't mean much, he's my father-in-law. Lara has done me a great pleasure of becoming a member of our external advisory committee in HAO, and is really a rock star in the area of technology, miniaturization, and CubeSat technology. And so I will hand it over to her in her presentation titled Using Small Satellites to Answer Big Questions in Solar Terrestrial Science.
Thank you. So in keeping with the idea of this session as a future-focused, forward-thinking session, this is going to be a very high-level talk. I'm going to try to make it as visionary as possible. And so with that in mind, I'm going to skim over a lot of details. I am by no means an expert in the dozens and dozens of small satellite missions that are either in development or currently operational. So I won't be talking about too many details, but what I hope to convey is this idea that the solar terrestrial community is poised for a potential revolution in the way that space weather research is conducted, provided that we are able to overcome some pretty significant challenges, observational challenges associated with these small satellite platforms. Now, as far as the big questions go, there is, of course, where do I point this to make it go? Oh, it's this one? It's not. I'll do it on I can do it on here. That's okay. Okay, so as far as big questions go, there's of course no shortage of them, and I found it extremely challenging to even be able to phrase just a couple to focus on for this talk. And so I cheated and stole these two from HAO's strategic plan, knowing that I would have a welcome audience, essentially. These are two questions of the four that were identified in the plan. This is the 2011 to 2015 plan that I found online. These are two questions that have a lot to do with essentially space weather, the impact of the sun on the Earth. Now, I know that a lot of you in the audience are much more interested in what's going on at the sun itself, and I will be mentioning that throughout the talk and bringing that back up towards the end. But as far as the science topics I'll be discussing in the context of these CubeSat missions and small satellite missions, there's really two. One is, what are the effects of solar variability on the near space environment? Short and long-term time scales, so going from the very intense response to geomagnetic storms to decadal time scales, planetary evolution time scales, having to do with either climate change or the escape, for instance, of our atmosphere into space. This involves both radiative and non-radiative impacts, so everything from the solar wind to the actual solar spectrum as it impacts the Earth. And of course, part of this is also really understanding what's happening in the lower atmosphere so that we can distinguish that variability from what the sun itself is driving. And then the second question is, has to do with small-scale structures. In the ionosphere, of course, there are numerous disturbances which disrupt communications, navigations. Equatorial plasma bubbles are one source of those. Gravity waves, of course, and tidal signatures. Tides being, of course, a much larger phenomenon. And then in the auroral zone, of course, it's very active. Lots of small-scale features there as well. The goal here is to understand how are these structures, where do they come from, how do they propagate, and then ultimately how do they affect the system as a whole. Now, as far as how we go about answering these questions, obviously space-based instrumentation is a wealth of value for the community. Obviously, it offers in situ sampling that's not possible any other way. And so here I'm thinking of things like particle detectors that would measure the solar wind speed, its composition, something sitting out at the Lagrange point, for instance, watching the solar wind come past. In the magnetosphere, particle detectors, ion densities, electron densities, and their energy spectra are vital. Obviously, precipitating electron flux in the polar regions. These are all types of in situ sampling that can only be done from space. Passive remote sensing observations can be done from the ground, but when you do them from space, you can see a much larger area. So large-scale Earth observation becomes possible. I've got a plot here of some GUVI data. This is the 13th, 56 angstrom emission is an oxygen emission, which essentially can be used to interpret it as electron density. This is a way of looking at the global electron density pattern. Each one of these, I don't know what just happened. Each one of these stripes, hopefully that won't happen again. Each one of these stripes is essentially one orbit of GUVI around the Earth. This is an instrument, the Global Ultraviolet Imager on the NASA's Time satellite. So one of these stripes is one away around the Earth. It processes very slowly, so it's more or less fixed in local time, but then the Earth spins underneath it, and you're able to build up a global map in terms of latitude and longitude of, in this case, electron density. Different wavelengths are governed by different physical properties and processes, so you can learn different things. But here you can see the structure, essentially. This is the electrodynamic fountain effect around the magnetic equator, including the South Atlantic anomaly right over here, this little perturbation. This is the kind of thing that's enabled by Earth observing passively with these air glow emission signatures. Thermospheric composition is another possibility, geocoronal density, auroral boundary locations. These are all things that can be done. And then finally, stereoscopic remote sensing, right? Putting more than one satellite up and trying to get a 3D perspective. This is something I'm sure many of you are familiar with the stereo mission, looking at solar coronal emissions, but it's also something that is being done currently with the TWINS satellites, looking at essentially ring current dynamics via energetic neutral atom imaging. So with that in mind, small satellites therefore offer an avenue to space, deployment of these sensors at a very low cost. The idea here is that the deployment mechanisms are now standardized. They're embedded on many, many launch vehicles, and then it's just a matter of hitching a ride into space. So the cost of launching, which is always the vast majority of the cost for these monolithic NASA missions, has now been overcome. The CubeSat protocol in particular has been very successful. It's in the nanosatellite range, just a few kilograms essentially. Each unit, 1U, is 10 centimeters cubed, and roughly about a kilogram. And there are now perturbations of these. They started off where they're all 1U. Here's an image of 3 1U CubeSats being deployed. But now it's much more common to encounter 3U or even 6U missions, roughly the size of a large shoebox. We used to call them the size of bread boxes, and we realized none of our students know what a bread box is. So we call them shoeboxes now. But the idea here is that by launching them as secondary payloads, it saves a tremendous amount of money. So for instance, the NSF CubeSat, if you win an NSF CubeSat proposal, you're looking at about $900,000 or so, maybe $700 in the early days. That includes the cost of the launch, which is much, much cheaper than it is for one of these NASA designated missions. Okay, so with that in mind, now that we have the rides to space, the field has turned to developing both the payloads and some of the hardware on the satellite bus, miniaturizing it, making it more efficient. And so this is happening in a very organic way. Everyone is almost working independently on various aspects of these problems. All the different kinds of detectors, photon, particle, and field, are undergoing massive evolutions in their designs. I'm sure many of you are familiar with the X-ray spectrograph that Tom Woods is working on. That's well underway, that CubeSat system. Polarimeters are now currently designed, miniaturized for Earth observing. I'm not sure of any that are being used to do vector magnetic fields for solar observing, but I'll pick that back up again down the road. Photometers, of course, are easy. They're already tiny. I should have even put interferometers on here, because interferometers, even though the field has gone in the direction of essentially making them have relaxed alignment tolerances. So instead of having something like a Fabry-Perot, where the smallest offset in your alignment will completely destroy your wind and temperature measurements of an air glow emission, by fusing essentially silicate prisms together, that's what's known as a spatial heterodyne spectrometer, you can turn what was a Michelson interferometer, where instead of moving the arms to build up the interferometric pattern, for your spectral line feature, you essentially put a fixed grating there. So it becomes all embedded, a monolithic device that fits in the palm of your hand. This is something that's also being done. Particle detectors, I'll talk a lot about an ion-neutral mass spectrometer, and of course electric and magnetic field detectors. All of these are currently ongoing, undergoing significant development. And at the same time, aerospace engineers, electrical engineers are working on the satellite bus components themselves. So power systems is a huge one, making them much more powerful and efficient. Attitude determination and control and communication systems, these tend to be very sensitive for CubeSat missions. This is something I'll talk quite a bit about. And then electronics, obviously, we would like to have rad-hardened systems be able to explore in different areas besides low Earth orbit. So with these developments in mind, usually the way that missions go about is you say, what's this great science question? Now let's go build what we need to implement and get the data that we need. This is a very common approach. This is the approach that we used for our first CubeSat mission. It was one of the, I believe it was number 6, funded by NASA, funded by NSF in their third round of competition. I believe they're now up to 5 or 6 years into this now. But the idea is that science requirements themselves drive the sensor development, which then drives the mission design. And so for an example, to illustrate this concept, our mission focused on neutral atmospheric composition. This is one of the hardest things to measure, very notoriously data-starved, and yet it's so vital for numerous space weather investigations. I've listed quite a few of them here. Obviously, the response to geomagnetic storms, I mentioned the OTA-N2 ratio as a metric of composition changes, but no one knows the actual oxygen density and the actual N2 density as separate species. All you can really measure is the ratio based on a ratio of air glow emission features. Ion neutral coupling. This is a nearly resonant charge exchange reaction between protons and oxygen, and the forward H producing, the forward in this case, the way I've drawn it, H plus loss mechanism, and then the backwards H plus producing mechanism. This is the dominant source and sink for protons in the topside ionosphere. And so by looking at the proton continuity, for instance, if you measure all of these species simultaneously, now you have a way of looking at flux gradients, for instance, between the flux of this being transferred, actual plasma transfer between the plasmasphere and the ionosphere. Obviously, tides and gravity waves have a lot to do with neutral atmosphere perturbations. Joule heating, photochemical charge exchange reaction rates themselves are things that you can start to constrain in an aeronomical way as opposed to depending on laboratory calculations. And then, of course, photoelectron flux calculations. The sun ionizes the neutral atmosphere. Knowing how many neutral particles there are would enable that calculation. So the problem here is that even Dynamics Explorer, which was this great mass spectrometer that was sent up, the DE2 mission hosted this, it was only in space for about 18 months, and it didn't measure hydrogen. And meanwhile, all we then have are remote sensing techniques, and as I mentioned, the most popular one only returns a ratio of composition. We do not have any routine, long-term global means of measuring individual species composition and densities. So our goal, we said, well, what do we need? We need another mass spectrometer. Absolutely, it's been a long time. That ended, the DE2 missions ended in 1983, right? It's been a long time since we had some new mass spec data. So we say, well, let's build a sensor for this. So we did. We called our mission ExoCube because we wanted to measure these where we admittedly have the lowest amount of knowledge, which is near the exobase. It's just a few species, hydrogen, helium, and oxygen, maybe a little bit of N2 and O2. Hanli had the composition plot. And so we put a team together. John Noto from Scientific Solutions, this is a small startup optical devices company, is the PI. NASA Goddard built the sensor. Cal Poly students built the satellite bus. And then the science team was led by me at UIUC, Ed Mierkowitz at Embry-Riddle, Bob Kerr at Arecibo Observatory, and Susan Nossel at University of Wisconsin. All of us exclusively, up until that point, had done remote sensing of neutral composition. And so this was our first experiment, essentially, with having our hands on some in situ data. So the payload is a dual aperture gated time of flight mass spectrometer. Sue did a great job of talking about the mechanics of how time of flight mass specs work. Essentially, ions and neutrals enter into the RAM, essentially cone aperture of the instrument. There are two of them. Dual aperture means that one is targeted for ion measurements, one is targeted for neutrals. In the case of neutrals, there is a retarding potential that filters out the ions. And then there's also an ionizing filament that then ionizes those ions in this chamber. And once they're ionized, they pass through a time of flight gate. They get bent around and measured on the detector. And in this case, they're energized across this potential drop so much more than their original velocity distribution corresponding energies that the time in which they arrive on the detector it's a function, of course, of their acceleration, which is a function of their mass. So you can see that this is how it ended up. It's just about 1.5 U. Our whole mission was at 3 U, so it fit quite nicely within our shoebox. And what the instrument's able to do is measure the density of all major ion and neutral species. So as I mentioned, it's hydrogen, helium, oxygen, and N2. Here is a laboratory spectrum. Now this was taken in a vacuum, which everyone knows is not truly vacuum, but you can see that we're picking up quite a lot of hydrogen. Here's our H2 and helium are, obviously aliased. And then you can see that starting to get into the molecular species, we get less and less separation. This is by design. As I mentioned, hydrogen's never been measured, so we wanted to make absolutely sure that our mass resolution did a good job of separating helium and hydrogen, which is something that DE2 mass spectrometer was not able to do back in the day. This would represent the very first time hydrogen's ever been measured in space directly. Our peak power was, well in line with something the satellite was able to put out. And then, meanwhile, we had a lot of control over the instrument itself. We weren't sure exactly what environment we were going to be encountering. No one's ever measured the densities before. So we made sure that our filament, we had control over that voltage so that we could ionize more or less of the neutrals to make sure we measured enough of them for a good signal to noise. The fact that we used mostly off-the-shelf hardware meant that we were able to fabricate this very quickly, and this is true in general of these small satellite missions. And this is a real advantage here. You don't need a long lead time the way that most NASA missions have been. And then meanwhile, it allows students to either, in some cases, lead the development of components and integration, or at a minimum participate in a really meaningful way. This is, of course, an NSF-funded mission, and this is part of the rubric, essentially, of NSF's mission, as well as HAO, of course. So this was a big deal that we had so many students participating out at Cal Poly, including, we also had some graduate students at some of our institutions lined up to do thesis work on some of the data analysis side of it. So here's a picture of the satellite itself. You can see we've got these booms on the side are for passive gradient control. This is a way of, gravity gradients. This is a way of providing passive control, so we don't need as much power. But we did have quite a lot of attitude determination and control systems for built-in redundancy. In this case, if we're not aligned right on the RAM direction, we don't know how to interpret our data in terms of density, right? You need to make sure that you're getting essentially all that you can measure. And so a lot of effort was spent on this, and numerous master's theses came out of this work. Communication, back when we proposed and started the design of this mission, communication systems were still in their infancy to some extent. And so we thought it would be very clever of us to use an amateur transmission band. And then we would have all of these ham radio operators around the world be able to pick up our data and send it to us. And that, to some extent, that's how it worked. I'll mention what ended up happening. But the trouble is that by transmitting at 430 megahertz and not knowing ahead of time how many ground stations you have, we only had the one we could count on, which was at Cal Poly. And so what that means is that we had a pretty small, pretty modest downlink capability as far as how much data we could pull down. And that ended up being a big issue. But with that in mind, in general, the way missions need to be designed is that they you must operate within your communication and power limits, but ideally you want to optimize your science operations. Okay, so in the case of ExoCube, based on the amount of data one spectrum required, we were able to say we can get roughly 600 to 1,000 samples a day. You say, well, what's our time resolution for a sample? We chose 1 second because we wanted to make sure, think of this, our satellite's going at 8 kilometers a second, so we wanted to make sure we had pretty high spatial resolution through some of these equatorial structures, through some of these auroral structures. But what that means is that we get, you know, not much data, not much time period of data in a given day. And that's okay, we have a 6-month lifetime. And so what we did is we designed a pretty sophisticated scheme where we would combine onboard processing, either binning of consecutive data to make sure we have enough signal to noise. There was some essentially lossless compression, that involves some statistical signal processing. We also designed it so that we would sample only certain places on the globe that were the most interesting, such as equatorial and polar regions, but also over every ground station we could get our hands on. So when we flew over Arecibo, we would turn on and observe continuously, while Arecibo's incoherent scatter radar and passive optics instrumentation would be turned on. Same with 4 or 5 other ground stations around the globe. And duty cycling, of course, of the instrument in a patrol mode type capability. So this ended up being quite a lot of effort. And in fact, when we designed it for the proposal, we then had to completely redesign it once we found out what our launch opportunity was. So a crucial take-home point here is that your operational design must be flexible enough to accommodate that kind of rethinking sort of mid-stride. So what ended up happening? Well, we launched after a 3-month delay at the end of January this past year. We were piggybacking on NASA's SMAP mission, Soil Moisture Active Passive, into a very high inclination polar orbit, perfect for our needs. It was sun synchronous, which dawn dusk is okay. We can take some ground-based optical data and still be okay with that. But we were really hoping to present in local time. But we got the elliptical orbit we really wanted. So we wanted to be able to build up altitude profiles of neutral density. This is also something DE2 was not able to do. Here's a picture X03 of our beacon call sign as observed by a German radio ham. So that whole thing about using the amateurs around the world really did work. Unfortunately, within just a few days of launch, it was noticed that our signal was really quite weak. So this beacon is a different subsystem. We don't actually communicate. The beacon is just broadcasting all the time. But the system, the antenna system we were using to send actual data back down to Cal Poly, something went wrong. It was determined that our antenna didn't deploy fully, and it was kind of kinked, much like Galileo had the antenna issue. And we thought, well, we can work around this, right? We just need a bigger receiver on the ground. We're going to make this work. And so we did. We found SRI generously helped us out quite a bit. We developed a receiver at Wallops, and we start taking data, and we say, okay, we're ready to start turning on the instrument. And so we did. First thing we did was to turn on the instrument without the filament and without the retarding potential. And so we got our first flight spectrum of ions. Unfortunately, we couldn't transmit enough data to know what direction we were pointing in, so this is not usable scientifically. And meanwhile, we were still tumbling. Okay, so we hadn't yet implemented our detumble scheme when this was taken. So the next thing we did was turn on our ionizing filament. The reason we didn't do the detumbling right away is that we thought, well, you know, if something happens and we put ourselves into this very fixed orientation, you know, towards RAM, not knowing what's wrong with the antenna, we might never be able to hear from the satellite again. So we want to test the instrument first. I mean, one of the goals of this mission was to increase its technical readiness level for future flights. So we turned on the neutral side of it, and we saw, you know, it's outgassing, of course. So we have some H2 and some carbon, which shouldn't be there in the upper atmosphere. But nonetheless, we saw the H signature we wanted. And we saw an oxygen signature, and we saw a nitrogen N2 peak. So we're extremely pleased with this. And so we waited about a month for the outgassing to go away, and then we sent the message to deploy the booms, and only one boom deployed. And very quickly, we were put into a position where it's true that we lost contact, and so now we have an orbiting satellite we can't talk to. So unfortunately, this is the extent of our conclusions of of where that came from. But the nice thing about these missions, and this is the whole point of CubeSats in particular, is that these are almost disposable sounding rocket type missions. They're just vastly more sophisticated. And so the fact that we even have a list of lessons learned is a tremendous accomplishment, beyond even the fact that now we have a sensor that we know is capable of doing the science that we want it to do for future deployments. So what did we learn? On the one hand, part of an issue that we encountered is that at Cal Poly, a lot of the student involvement was through a course that was offered, a CubeSat development course. And so what happens is students come in and they work on the design for one semester and then they leave. And then the next group of students comes in the next semester. So having that knowledge transfer in place and having a continuity of expertise was somewhat challenging. And so next time, we would like to, while the curriculum-based involvement I think is important, you also want to make sure that there's sufficient involvement at either the graduate student level or capturing freshmen to work on it so that they have at least the full 4 years of their college program to be involved in the project. Testing. So the testing is an issue. Testing is one of those things that's not really compatible with the CubeSat idea of CubeSats in the sense that these are almost throwaway missions. There's no time or really money in the budget to do a lot of testing. However, it is important, and I think it should have been more prioritized in our case. What ended up happening is that the euphemistically called nylon monofilament, also known as fishing line, didn't burn the way it was supposed to. And we think that what had happened is that after our shake test, getting ready to go into space, it had been knocked loose. It wasn't loose enough that we failed the shake test, but it was loose enough that once we finally got into orbit, the heating element was no longer in contact with the wire. So that's the kind of thing we could have tested more had we had the time. And so I would encourage, even at a programmatic level, to allow for this kind of testing to take place. Another one is component redundancy. Again, it's not really compatible with CubeSat missions, but in order to enhance science return, this is going to be essential. One thing, our ground station contingency plan, when our ground station couldn't hear the satellite, it took months to set up and arrange other ground stations. So having a contingency plan in place is something we'll definitely do in the future. And then launch delays, better preparing for the launch delays. We had an instrument that's sensitive to humidity sitting on the tarmac without power for 3 months. And so that's something you definitely want to be able to avoid. We had given it a nitrogen purge. We do expect that it all leaked out, hence all of the H2 we saw when we finally exposed it in space. Okay. Another approach, the last thing I want to talk about with the remaining time is that being that's sort of the old school approach to mission design. You have a science question. We're going to build the sensor to answer that question. We're going to deploy it and hope that we deploy it in the place that we want. You don't have a lot of control over launches. That is, in fact, the bottleneck of all of this still remains the launch opportunities. And so a new approach that I've taken recently is that when a launch opportunity presents itself, design the mission to optimize the science that can be done for the launch that you're going to be given. And so the example I want to use in this case is the upcoming Exploration Mission 1 launch. So this is the first planned flight of NASA's Space Launch System. It will be the second uncrewed test flight for the Orion spacecraft, the new manned spacecraft. The launch is projected to occur in September 2018. The spacecraft itself will essentially be launched and then go around the moon a few times, and then in a circumlunar trajectory. But along the way, these secondary CubeSats will be spit out, bam, 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 along the side, right around 5.5 RE. Now, once they get in that position, they've got this forward velocity towards the moon. This will be roughly new moon, so they're heading right towards the sun. They'll do a gravity assist around the moon and then get launched into a heliocentric orbit. We said, what kind of science can you do with an orbit like that? The answer is the hydrogen geocorona. I mentioned before, we've never measured hydrogen before. This is a perfect opportunity. We're going to be going right through the full extent of the geocorona and then end up outside of it looking back at it. So its global structure is something that has been very hard to determine. And you say, well, what's the point, though? You know, just because you can doesn't mean you should. And so I want to take a few minutes here to talk about why hydrogen is so important. This is actually becoming the bulk of my research here at Illinois. Neutral hydrogen, and the ionization of this is the primary source of total electron content. So if you're interested in TEC storm variations, understanding how much hydrogen is there in this upper thermosphere, lower exosphere region is absolutely vital. Meanwhile, it readily escapes from the Earth. And so it plays an important role in the long-term evolution of our atmosphere. Bob Kerr once explained this as the oceans boiling off, right? You have a water molecule, it dissociates into 2 hydrogens and an oxygen, and then your hydrogens fly off into space. That's water you're never going to get back. Another point here I had mentioned earlier was the charge exchange. The charge exchange process, within about 1,000 kilometers, or really within at least a few RE, is what generates the E and A atoms, those energetic neutral atoms, kinetically energized from the charge exchange process, that are then imaged by twins in order to learn something about the ring current. That dissipates magnetospheric energy after the solar storms. So this is a big player. This process is a big player in storm time evolution. And then meanwhile, it enhances that escape of hydrogen. There's an interplay here between the thermal expansion of the Earth's atmosphere and this non-thermal process. This is something we don't understand at all, how the relative significance, I should say, of these two processes. Meanwhile, solar radiation pressure. These are long-lived particles in highly elliptical orbits around the Earth. There's a bound population that extends out to about 30 Earth radii. And so the radiation pressure can perturb this and create a structure that's extended along the Sun-Earth axis, which then feeds back into the creation of these energetic neutral atoms, and therefore the interpretation of E and A images in terms of ion densities. So this is a complicated project. I've tried to sum it up here. This took a long time to think about here. But we've got important roles in the MLT region. Here's that charge exchange in the thermosphere, ionosphere, also in the exosphere and plasmasphere. And just trying to identify, what are these thermal and non-thermal processes. Ultimately, you can see that H neutral hydrogen plays a significant role throughout this region, from the mesopause out to the magnetopause. So we definitely want to study it. And then the trouble is, we really have such a limited idea of what's even going on. Routine estimates are being obtained near 90 kilometers by the Time Saber instrument. That, though, is done by measuring ozone emission, for instance. So there's a lot of chemistry involved in interpreting that data. Meanwhile, it doesn't tell you enough of what you need to know about what's going on in the exosphere. At high altitudes, TWINS does have a Lyman alpha detector, so it's a photometric detector. You can interpret it in terms of H density, but in that case, they tend to assume, you have to assume some things in their analysis of this data. They assume, for instance, that there's a spherical harmonic truncated at the second order spherical harmonic distribution with a certain exponential decay profile, for instance, and then they fit the coefficients. So it's a little limiting. Meanwhile, they have to use models for what's going on with the solar source emission and the interplanetary background. Here's an example of the kind of things we have, though, figured out from TWINS. These are contours of constant H density. The sun is in a different place. I apologize. These are from 2 different papers. The sun is in a different place, but nonetheless, these are meridional scans looking down in the equatorial plane. Here's that sun-Earth alignment from the radiation pressure I mentioned. This is a seasonal average of 3 years of TWINS data. Here's 1 day of data. And these have a very similar analysis approach. And so what that says is that, wow, you can have some pretty significant time variations here. We don't understand what drives those. So our mission, we called it the Tomographic Hydrogen Emission Observatory. THEO, this was a partnership between myself, I was the lead on this one, SRI and SSI, Scientific Solutions, again, John Noto, were the payload developers. That was it's a Lyman alpha photometer. UC Berkeley was going to build the bus. And the bus itself, we're going to have this photometer. Here's the field of view of photometer, essentially at a controlled rotation nutation. type paradigm. And it was a 5-minute period. So very, very slowly, very controlled, 3-axis stabilized. And by doing that, we would have lines of sight as the satellite moved through the system that overlapped, and now we can use tomography in a model-independent way to estimate this distance. And so this concept of having a spinning or a rotating platform, it's very well suited for tomographic sensing. Here's the integral equation for a single measurement where you have an emission intensity along a given line of sight. It's an integrated quantity. It's a function of your densities along that line of sight and some sort of a scaling factor essentially to do with your solar strength. And what you do is you discretize the unknown, the hydrogen density, in terms of a matrix H, for instance, and then a matrix L is your viewing geometry through that system. And this vector I here is then all of your measurements. And you stack them up in a vector. And then W would be noise, for instance, Poisson noise, and then you invert it for the unknown H. And this is something that's very successful. Here's an image we've assumed. This is one of the spherical harmonic distributions. It's actually the one with the contours I showed earlier. And this is reconstructing it without taking any a priori knowledge into account. This is pure Tikhonov regularization here. We can, in fact, by saying we know densities are going to be positive definite. We know that they're going to be very smoothly varying, for instance. We can start to even improve what we see here. This is an approach that's actually quite well suited for CubeSat platforms. In low Earth orbit, in fact, one will be launched soon, whereby the satellite itself spins. And it spins very quickly because in low Earth orbit, of course, you're moving much faster. And so you spin very quickly, and you can see how the lines of sight overlap. This is not a new concept, but it will be new for a CubeSat. And so this is the NSF, it spins. IT stands for Ionosphere Thermosphere, but it's a cute pun. I always loved that name. It spins CubeSat. And you can see that if you start to have this kind of observing modality, and you build it up into a constellation or a distributed type sensing capabilities where you're using more than one satellite, for instance, in a sun-synchronous orbit at different local times, now you're able to really get somewhere when it comes to Earth observing. And so here you can see just some simulation results. This says, oh, you know, if we have 6, for instance, and we assimilate those 6, we can do a much better job in estimating O to N2 ratio, for example. Back to Theo, this is one of my last slides. As always, as I mentioned before, you have to balance power and communication capabilities with the science goals, things that you want to achieve. And for this translunar mission, this was a really big deal. We wanted to be able to hear from our satellite out at 300 Earth radii, 400 Earth radii, and we are quite confident that that's entirely possible. So we did it using Allen Telescope Array initially, and then the Arecibo Observatory once it became visible, essentially. And so we can see here's our channel capacity. As the satellite gets farther and farther away, we have a programmed rate reset of how much data we try to send down that pipe, essentially, in order to accommodate that decrease. And here's where Arecibo kicks back up, so we jump back up. The problem here is that power, communication, and then ultimately the science that you can get from your sampling rate, they're all intertwined. And so the science drives your sampling rate. You say, well, I'd like to have as high resolution data as possible. And then the sampling rate drives how much data you actually generate on board as a function of time. And that drives your transmission strength and duty cycle that you need in order to get all that data down. And that drives how much power you need to run your transmitter. And then the power you need that's power you don't have left over to operate your instrument, which means you've got to cut back on your sampling rate. So this ends up being, this is the kind of thinking, though, that has to take place when you design these instruments, is to do essentially a trade space analysis. So here you can see it's our data generation rate, some sort of margin, power margin, and then this EB to N0, this is a metric, essentially, of your communication quality, some sort of a noise level. And so that has to be, that definitely has to be something that's taken into account. But the bottom line, this mission that I'm describing here was submitted initially to NASA as one of 11 missions for the single heliophysics slot, CubeSat slot on the EM1 satellite, EM1 rocket. We were down-selected with one other team, and eventually we were declined, but I feel pretty good about how far we got and knowing what's capable, what we're capable of and what the communications are capable of is something that's definitely optimistic for the future. So just as a way of summarizing a visionary type statement, small satellites are certainly poised to make great contributions to solar terrestrial research. All of these hardware and payload advances will mean that we can increase the diversity of payloads. I'm thinking in particular of imaging systems. This would be highly relevant for solar research. To date, that's been the communications has been the bottleneck on that, trying to get down that much data in a skinny pipe. But antenna development and ground station infrastructure has come a long way. And so that's almost a problem that's almost overcome. Meanwhile, propulsion systems and some of these interplanetary launches, being able to communicate at large distances means that solar system exploration is now a possibility. It's entirely feasible to say, I would like to put a CubeSat at the L1 Lagrange point, and not a problem. That's something that can be done now. I don't know if you want to stick an imager on it right away. You might want to keep your data stream a little bit low. But nonetheless, the future is, if this is on the horizon. The miniaturization is, of course, only going in that direction. There's talk now of what's called satellites on a chip, where you essentially populate space with satellites the size of your fingernail. But even intermediate sizes, around 1 kilogram or so, half a kilogram, is something that's very much under development in a realistic way. And then the last thing I want to mention is that launches are still the bottleneck, by far, the vast bottleneck to this process. And so, being able to put more CubeSat P-pod, for instance, deployment schemes on the launches, having more launches, privatizing launches, that kind of thing, will enable distributed constellation missions. This is the kind of thing that would really open the door for solar work in particular, being able to have multiple angle viewing of the sun, for instance. So I'll stop there. I know I've run over a little bit, but hopefully I've convinced you that this is something it's definitely worth keeping your eye on in the years to come. Thanks for your time.
Thanks, Laura. It's really very, very innovative, and these are pathways we should all explore, I guess, as to try and drive costs down of missions and still have fairly significant return. So, any quick questions before we break? Very quickly.
I understand there was a CubeSat on that failed launch by Orbital Science Corporation that blew up on the launch pad. And I saw a quick message that the CubeSat survived and was washed ashore recently.
A water landing.
Do you know details?
I don't know the details of that, unfortunately. I do know that more than half of CubeSats that are currently operational are essentially private commercial use as opposed to science use. I don't even know if this one was a scientific CubeSat or not. Most scientific CubeSats are launched through what's known as the ELENA program, Educational Launch for Nanosatellites, run by NASA. So this being a potentially private, was this a NASA? I don't think this was a NASA-based launch. But no, I'm just speculating. I honestly don't know.
Any takers? Last one. Ricky. All right, and then we're good for a break.
So the Planetary Society recently had a 3-unit CubeSat called LightSail. It deployed 32 meters squared solar sail. So they weren't at an altitude where they could actually do navigation. But the idea is one day you have this point there, low power propulsion. That's zero power propulsion. Mm-hmm. I think it's a very exciting possibility for solar to get into sort of highly inclined orbits, non-Keplerian orbits. Have you heard of anybody working on the combination of something like a CubeSat package and a solar sail propulsion?
That's a great question. I haven't but I do know where to point you as to who would be working on that. So there's two things going on. Every year there's a CubeSat conference at Utah State, and they put all of their materials, their talks online. And it includes everything from power system development, attitude control, to the payload, to ongoing missions. It's a smorgasbord, essentially, of everything CubeSat. The other area is that right now, actually, this week is a National Academy of Sciences sponsored meeting on CubeSats. It's a symposium, essentially, on what's possible and the kind of technologies. It's meant to be extremely visionary for shaping the future direction, and this is exactly the kind of thing that would be talked about there. So I can show you where to look that up, but I wouldn't be surprised at all if even more than one team is working on something like that now. You know, this is a very, it's an organic, I mentioned earlier, an organic effort. There's no one lead doing all of this development. Individual PIs essentially are doing all of this on their own in an uncoordinated way, but ultimately highly productive. And I think the goal in the future will be to bring together, a bit like herding cats, but to bring together all of these cutting edge technologies into a package that would rival even some of the largest NASA missions.
And with that, I thank Lara again